Okay, we've got two programs here, design tool 2D and 3D. We're going to start looking at the 2D. It's an environment that's really good for demonstrating some of the basic principles of how loudspeakers interact with each other. So here I have two subwoofers. These tiny little dots here, we can zoom way in and see what they, but basically we zoom out. Here's two woofers tight packed together, and of course we understand that that creates a nice omnidirectional field. We can then move them apart, watch in real time. Frequency response changes from the bottom of the screen. And of course, if they get really far apart relative to the wavelength, and we replot that, we get our friend the power alley. This is stuff we all know. It's just a great way of doing a fast demonstration of it. So we have representation of subwoofers. We have our TH118, which is a single 18 tapped horn, the DBH218, which is a direct radiating horn, and the 812, which actually does have some forward directivity due to the size of the boundary, and will give you an idealized omni to play with too. This is a great program for messing around with cardioid arrays and phased arrays, directional arrays, and so forth. All of the loudspeakers that Danley builds that have been independently verified or independently measured are also included. Remember, this is a 2D environment, so when you're messing around with loudspeakers, you have the choice of using side view or plan view. You can do mapping in 2 dimensions. Let's look quickly at the 3D. 3D is a similar architecture. We have our sound plan over here, our frequency response window down here, and all of our controls over here. One of the big differences between 2D and 3D is that 3D requires an audience plane to project onto. So I built a little wireframe building here that has no acoustic properties at all. This is just eye candy. And if I ask it to map, it won't, because there's no audience plane. If I include an audience plane, which is this dark line here, I can then map the coverage onto it. Like in 2D, I can put microphones. Out here I've set a bunch of microphones around, which are sort of my target microphones, I call them. So as I'm designing the sound system, I can in real time look down here and see the frequency response at 5 different locations in the room. One of the cool features of this program is this semicircle of mics. So we have our target mics out here, but if we wanted to explore, some area of the room where there might be a cluster and see how that cluster works, we can turn on a semicircle of mics at any point in XYZ coordinates, and it'll show the response of this semicircle of microphones down here. When we turn that off, our target mics come back. We can look at 2D views down from the top, from the side, or from the front. And we can also use this 2D environment to send coordinates to any device we wish. So for instance, if I want to put a loudspeaker here, I can simply, you notice down here we've got X, Y coordinates that move as I mouse around. When I click on a position, these boxes will capture that position, and then I can send that wherever I'd like. If I want to send that to speaker number 3, for example, bang, there's speaker number 3, and you can immediately see the wonderful impact that's had on our frequency response down here in the frequency response window. Of course, speaker number 3 is probably sitting on the ground since I didn't give it a Z location. There's one left over from before. Okay. Let me talk quickly about, let me turn off 3 because it's really ugly. There we go. Let me talk a little bit about the laser beam. You see this line coming out of our loudspeaker with the red dot down here. When a loudspeaker intersects with a audience plane, it creates a little red dot. You notice if I change the inclination of this, move it up so that it doesn't intersect with an audience plane, the dot goes away. When I bring it down and it intersects with the audience plane, we have our dot. If I click on laser info, this tells me that intersection point. So the program captures the XYZ location of the loudspeaker and of this intersection point with the plane. All this is captured and presented in a report that's generated automatically by the software. So if you have a big system with a lot of speakers, a lot of audience planes, all of the aim points are captured in the report. What am I forgetting? I don't know. A quick caveat. The program is not an acoustics program. It's simply a direct field calculator only, which is fine for 99% of what you're doing. The only thing it doesn't do well is it doesn't model balcony shadowing. So if you have a church with a balcony, it won't capture the fact that the balcony shadows the plane below it. We're working on a workaround with that. I don't want to build an acoustics modeling engine here because that's not what we do, but we're going to think of a way to do that, hopefully a clever solution for that. But right now that's the one gotcha. If you're modeling a room with balcony, it won't accurately capture the shadow of the balcony. Beyond that, it's a pretty good program. And if you have any questions, I can be reached at Doug@DanleySoundLabs.com, and I'll try to answer them.
Thanks a bunch, Doug.
My pleasure.